Easier to hear what I have to say when my mic is on. Hi, everyone, and warm welcome to our Composite Talks. My name is Linnea, and I am the representative of SWE-CIC, Swedish Composite Innovation Cluster. It's now 2 o'clock, and I'll give it a few more minutes, maybe, or before we get going. Anyway, I'll introduce you to SWE-CIC. Meanwhile, people are keeping on dropping in. SWE-CIC, Swedish Composite Innovation Cluster, that is our composite innovation cluster here in northern part of Sweden. We want to challenge the future, and we want you to challenge the future with us. We believe that fiber composites is material of the future, and hope that this will inspire you as well to see what we see. SWE-CIC is a part of a project that is funded by the European Union and the Regional Development Fund, as well as the Norrbotten region, Sparbanken Nord, and the municipality of Piteå. We're very thankful to our financiers. Further on, a bit more about SWE-CIC. This is our members. We are everything between, from big corporations like Hitachi Energy and to small companies like Blade Solution that you will listen to today. We also have Luleå Tekniska Universitet as well as RISE with us, so we have a lot of scientists with us. Anyway, within SWE-CIC, we are about 300 professionals. We've been working with this for over 70 years, and we have been producing about 10,000 units per year in fiber composites. Some of the success stories, Greger in Blade Solutions, that you will, as I said, that you will listen to later on. He has his patented technology, and he also is nominated for an innovation award at the SWE-CIC later on this year. Yeah, so we're kind of a small cluster, far away from everything, but our companies are very talented and knowledgeable. So what do? We work with development. We help companies speed up their innovations. We have a test bed that is open access, that to you, and if you have an idea or that you want to develop or you want to try out something, don't hesitate to contact us. We can guide you all the way. And we can also help you with the production. We have knowledge within most of the production, the different types of production methods that are normally used. And yeah, if you want to contact us, this is our contact details. And we will also be attending SWE-CIC in May, given that there won't be any COVID and that Putin is behaving. We will also be in Gothenburg in the beginning of April at the Lighter International Conference. Anders, that's your cue. You are responsible for that conference, aren't you?
Oh, at least one of the sessions. Okay, great, Linnea, thank you. Composite Talks. Today, this is our 4th Composite Talks. Normally, we have Anders Breitholtz, who's the moderator, but he has unfortunately been heavily involved in a startup company that he's a part owner into. So his time has been limited. So I'll be taking care of the moderating today. Today, we'll be focusing on the wind industry. This is a super interesting area where composites has a very essential role. I mean, the purpose of these composite talks is to inspire and demonstrate and show where and how composites can be used for to really make changes in industry. And the wind industry is really one of those industries where this has been demonstrated. We have a really interesting panel today where we've been able to gather the complete value chain. We have, first of all, Vattenfall, we're speaking from a consumer and the marketing point of view. And then we'll have Diab, who'll be presenting a little bit more about the material and the technology of the wind turbine blades. And then moving over to repair, then this time we will be having one of the SWE-CIC companies, Blade Solutions, where Greg and Nilsson will be talking about repair and the technology that they're using. And then we'll end up with Siemens Gamesa, who will be talking about recycling of wind turbine blades, which is a big challenge, and how Siemens Gamesa has addressed that issue. So with that said, I would like to start off to invite Mikael into his session. Mikael is the Director of Industry Recarbonization or Decarbonization at Vattenfall. So I'll leave it over to you, Mikael.
Thank you, Anders, and thanks for inviting me. Let's see if Friday afternoon allows me to be in the mood to handle the technology here. I hope you see my slide now.
Yes.
Brilliant. So thanks for this kind introduction. I will talk a bit about a dual perspective of the energy company. As Anders mentioned, I'm Director Industry Decarbonization in Vattenfall, and that means that I'm responsible for developing partnership projects with basic industries, heavy industries, to help them get rid of their use of fossil fuels. So we're actually on one hand a supplier to the industry, and on the other hand, our tool to do that is primarily by the supply of fossil-free electricity. So there, in a way, we're a customer to the same industry as well. And I will try to dwell in a bit into these two perspectives, and in particular, what it means to composites, and most notably carbon fiber, that has been a specific interest of ours. I won't bore you too much with what Vattenfall is. I would, in that case, recommend to go to our homepage, but we can say that what condensed to its essence of what we're doing is that we want to achieve a fossil-free living within one generation, and we believe that being sustainable is a prerequisite for, in one generation from now, still being in business. That basically goes through everything we do right now, and I will go through a bit why and how that happens. First of all, why we as a power company see that we can play a role in this far beyond our own operations, how we team up with industries to get rid of emissions beyond what we do ourselves in the power sector. A bit specific on why we have started this in Sweden, and also these dual roles that I mentioned, as a supplier to the industry of fossil-free energy, and on the other hand, as a customer of what's coming out of the industry and those value chains. And then finally, a few words on why it will mean a sound business long term, why we believe that. So if we start briefly with why electrification, well, this is truly a depressing picture, I realize that, but the fact is that still today about 80% of all energy consumed globally is fossil fuels. And although renewables is steeply on the growth here and on the increase, we have lots of things to do when it comes to replacing the fossil fuels. And in several sectors, we know how to do that, but I will focus on the ones where it's a bit harder, and therefore they typically label the hard to abate sectors. If we envision ourselves to be mid-century and look at how can we possibly get rid of the use of fossil fuels? Well, if we need to replace that energy in all its applications, be it in heating, be it in power generation, be it in transport, be it in industry, we believe that the most promising solution we have is to do it with fossil-free and renewable power. Wind and solar has shown tremendous cost decrease in the recent decade, and it's also pretty quick to big, and we can really reap the benefits of manufacturing economics when expanding that. So this is basically our best shot, but it will be quite dramatic if we are to replace those vast amounts of fossil fuels. Some estimate up to 5 times more power production than we have today. The lower end of the scale here to the left is depending on how successful we are in becoming a more circular economy. So it's really no contradiction here between the circular economy and energy efficiency and shifting to fossil-free and renewable electricity. We need to do both, and the more successful we are in efficiency and circularity, the less prime power is needed. Now, square electricity doesn't fit into round applications everywhere. So an important part of this electrification, we believe, will happen as electricity is converted to hydrogen. And hydrogen can then have a role to replace fossil fuels in primarily lots of various processes in the industry. And going into a bit to what we're doing then in the industrial partnerships, these heavy industrial processes that we're focusing on is primarily the ones that are doing basic materials. Steel, cement, and plastics are responsible for not 20% of the emissions in industry, but 20% of the global emissions. In Sweden, that's no exception. It's about 1/3 of the CO2 emissions that comes from the industry, and 85% is in steel, cement, and petrochemicals. So if we target these, then we have a big part of the solution. And as I said, fossil-free electricity could be applicable in some way, but here we distinguish where we can use it, for example, for heating and motion directly, or where we first need to convert it to hydrogen, and that's what we typically label indirect electrification. The most visible project we have in this type of cooperation with industry so far is known from northern Sweden. It's a hybrid cooperation where we are working together with LKAB and SSAB with the purpose of converting the value chain for making steel and totally removing the use of coal in that. And we're quite well on the way here. We have actually already produced the first tons in our test plant. So this is kind of a model project for how we also want to approach other industries. And why is this happening in Sweden? Well, if you look at it, we have a very beneficial situation to start out with. I mean, this is some sort of Hans Rosling Gapminder wannabe attempt, and it's really complex. But if you bear with me, what this is trying to explain is the situation of the power system in Sweden compared to other countries in Europe. And to go through it really quick, I'm not sure if you're distributing the slides afterwards, but the more to the left you are, the cheaper the power is. The more to the bottom you are, the cleaner it is. The more green it is, the more surplus you have in your country of electricity supply. And the bigger the dot, the bigger the system, basically. So Sweden is quite in a unique position of having lots of access to clean and affordable electricity. And that's why we see the development starting here, because forming these new value chains, if you have a power dependency of power, at least that part is becoming less risky. Apart from this situation, we also see in the upcoming years that, not least because of the wind power, we will have a further increase in the electricity supply, primarily in northern Sweden. And that is mostly due to that we have now learned to build wind power primarily so cheap that it doesn't need subsidies anymore. So this is happening by itself. But of course, when you see this virtuous circle of industries now asking for more fossil-free electricity, this growth is even stronger. So a bit there, I've already touched about it in our role as a supplier, but what does this mean then specifically for the composite and carbon fiber industry? Well, if you look at how it's typically done today, you crack naphtha into the basic olefins, and this is where the major part of the emissions along the value chain is. And this is where we believe that we can take a stab on how to fundamentally change things. What we're suggesting that you could do is that you can start with a carbon source that is biogenic CO2. We have 35 million tons coming out of pulp mills and biomass CHPs primarily in Sweden today. And combining that carbon dioxide, which you can see as depleted carbon source, with an energy-rich hydrogen coming from electricity, you can then form in various basic hydrocarbons, which you can then process into olefins such as ethylene and propylene. And this just an example of how to do this, that is technology that is today known, is, for example, by forming methanol and then process it further through methanol to olefins process. And if you look at that full value chain, if you manage to do this and you handle this first part of the chain, well, you can follow here what happens. Once you get to propylene, you can then basically have a plug and play process to what already exists today, further into acrylonitrile, AN fiber, and then PON fiber, and then finally carbon fiber in the end to its applications. This way you would never mess with the qualities of the carbon fiber because you're using the same kind of base chemical as you do today. And also, if you're doing this large scale, the area requirement is hopefully quite minor. Turning around then, if this carbon fiber is embedded in blades and built in wind power plants, this comes back to us in the other end as a customer. And if you look at the carbon footprint today of wind power, which is somewhere around maybe 7 grams of CO2 per produced kilowatt hour, since the fuel is free, it basically boils down to the embedded emissions from the materials and the manufacturing process. And the major part there is steel and cement. As you saw from the hybrids slide, we are already on to producing steel without footprint. Cement, in case you have that kind of foundations, we're also looking into, and with the refinery processes and what's happening on the west coast of Sweden now, also HVO as a replacement for diesel is on its way. And then what is left is basically the carbon footprint of the blades. So the more we're successful with the other basic materials, the more the attention will come to plastics and composites. And if we look at the investment plan that Vattenfall has now over the upcoming years, I don't have the latest figure, but it's pretty similar in the same direction. A majority of our growth capex is going into wind power. As you see, there's 71% or 23 billion SEK over the 2-year period of 21 to 22. So we are at a pace of about 1 billion euro per year investment. So these things matter, and we have third-party reviewed our goals in Vattenfall to be in line with the Paris Agreement, and we're also now starting to put requirements on our suppliers to start to reduce their footprint. We want to cut the scope 3 emissions of Vattenfall in half to around 2030. Finally, a few words on why we think this is a sound business case. Well, it all boils down basically to the value chain logics here. If we look at these crude materials that we are producing, you could envision that a cost increase in those would basically kill the business case. But if you pick one of these as an example, steel has a market price which is about half the price of potatoes. So it's a really cheap material, and adding maybe 20% on the cost, which was an initial estimate in hybrid, that would add about 100 euros per ton of steel. Now, if you turn a ton of steel into a car, and in the end, the 100-something euros comes on top of the price tag of the car, then that is becoming really marginal on the product level. And I would argue that the same logic here would go for fossil-free materials going into also wind turbine. In the end, the cost of the wind turbine is of course somewhat more expensive, but if you look then in the end of the levelized cost of electricity, the effect on that is actually quite marginal. And it's also becoming a selling point to be the ones now with the prime carbon footprint behavior, so to say. We also see that customers actually start to value this. So even if regulatory systems are too slow, there is a pressure on the customer side, which we have seen and experienced, not least from the hybrid project, where we already now have customers lining up to buy fossil-free steel, despite it might be somewhat more expensive than conventional steel. So this is, I hope that was kind of useful, the perspectives of the energy company, both from a supplier perspective and a customer perspective. And I'm happy to have either any questions now, Anders, if you were thinking about that, or we save that for the panel discussion. I don't know how you want to do it.
Okay, thank you, Mikael. Linnea, I don't know if we have received any questions, but otherwise, regarding the low cost energy that we have in Sweden, do you see a trend of bringing companies back to Sweden? Because I know, looking at the energy mix that is, for example, in China, where a lot of the composite production is today, is really detrimental from a life cycle analysis point of view. Do you see a trend in companies being more interested in bringing production back to Sweden?
Yes, definitely. I mean, we've seen this trend for a couple of years now, especially to northern Sweden. The hybrid project is just one example. There is a similar greenfield project for steel in Boden, H2 Green Steel. We have seen Northvolt set up a battery factory in Skellefteå. There has been an international fertilizer company testing the grounds in Luleå for an ammonia plant. So all these really energy intensive industries, they are looking at Sweden right now. So Norrbotten is the place to be.
Yeah, I wonder, we've all read that in the news that it's going to be a tremendous development in Norrbotten, and challenges for everything from schools to hospitals to school to everything basically. Yes, Linnea, did we have any questions? I saw that Khaalid raised his hand very shortly there. I don't know if you.
Yeah, no questions yet. But I think that we might save the questions to the end.
Okay.
And so that we have the panel discussion in between everyone.
Okay, that sounds good. So then we thank you, Mikael, very much. And regarding sharing presentation, we are recording the presentation. Will be sharing as well, Linnea?
Yes, and we will upload it to our YouTube channel.
Perfect.
Later on.
Perfect. Okay, so that was the perspective of the market and the customers, and now we want to move further along the value chain and looking into the material side. And I want to welcome Mr. Ray Lewis, who's the market segment leader for wind energy at Diab. And I know that you have a very long experience of materials and the wind turbine industry. So it's going to be very interesting to hear what you have to present here. So I leave it over to you, Ray.
Thank you very much, Anders. I certainly felt very old then.
That was not my meaning.
No, I know. But my colleague who's listening on the phone is certainly for sure going to use that for the next week.
Okay, okay.
Can you see? Okay, let's just make sure you can see my screen, I guess. I need to go in presentation.
Yeah, exactly.
Is that okay now?
Yep.
All right. Okay, so first of all, thank you for inviting me, and thanks to everyone here who will also listen. So by view of just a quick introduction following on from Mikael's presentation. Modern day wind turbine generators, I mean, they use composite materials, shall we say, in three main areas: the blades, the nacelles, and the spinners. And the following slides cover all of those, but I focus really on the blades, which is the largest area for sure. Typically in these applications, we use there's a sandwich structure used, which uses, you know, resin impregnated fiber, either side of core material, of which, as it says here, you know, Diab has been a supplier really from the really early days. Traditionally, Diab was one of the original PVC manufacturers in the world, which you know, came as a result, you know, the industrial area around the Second World War. And then basically the company has grown from there. PVC got used into the marine applications. We got a lot of knowledge, and then it was transferred basically to wind when that market came on. So if we look at the nacelles and spinner market as just as a very quick overview, most of these structures are effectively, you know, they are non-structural. If you go back a few years, a lot of them were metallic, and they progressively got replaced, either with single skin composites, sandwich composites, where core got introduced. And they've mainly, again, been non-structural, although some designs have actually become structural, so they've actually called for different materials. And if you look at the materials that have been used in there, typically they've been relatively low density materials, 45 kilos per cubic meter PVC, and then the 60 kilo on the structural designs. Then I think, you know, we've all gone through various sort of evolutions over the years, and costs became a really high focus when the market grew several years ago. Polyurethane became quite an attractive material because of its low cost base. And again, should we say relatively low because of the non-structural requirements. And then really in more recent times, you know, as a result of cost changing, PU wasn't as competitive. PET came in as a, you know, really as a sustainable material, which I'll talk about more on the following slides. And that really has become a little bit of a default material to be used really in these applications. Typically, you know, around 60 and 80 kilo per cubic meter PET. Initially, we could say virgin material, and more recently recycled, that have come from the likes of, you know, post-consumer bottles of PET, etc. And I think it's just maybe one thing to see on here. You can see the different densities of PVC mentioned against PET. So typically to produce a material with similar properties to PVC, you need to have a higher density. And of course, that brings with it some benefits, but it also brings with it some disadvantages. And then it's a question of what is the main driver for the end user. So if we drop down to blades, it's obviously a similar situation with resin, the reinforcement and core. And here I'll just go into the core material in you know, in a little bit more detail. The range here tends to increase, as you can see, from 60 now up to 250 kilo density PET, which is being used in very recent times. So those have become the, if you like, the default materials. There's been fundamentally those that sandwich structure has remained the same in these horizontal axis wind turbines. And we see changes, you know, I think for the same reasons that Mikael showed in his presentation. resins have been changing. They've mainly been epoxy, vinyl ester coming in, and now people are looking at what's the next sustainable material. And of course, there's the movement that I think everyone's familiar with as carbon has got introduced as the blades have got longer. And we've seen really the same on core materials, which is what I go through in a little bit more detail today. The process that typically is used today is the infusion process. In the past, people will use wet layup, and I think you're all familiar with one not so far away that started using prepreg. It's still used today, but it's infusion that really is used everywhere. And for us, actually, at Diab, and for other core manufacturers, it's actually been a real benefit in some ways because, of course, primarily the core material is in there as as a structural core material to actually reduce the laminate weight. But the other part, which is not often seen, is it's acting as a processing aid during the infusion process. So, typically in an infusion process, you use some form of medium, a mesh, to transfer the resin. And one way you can do that really cost effectively and more sustainably is to actually put appropriate grooves into the core material and get that to be used as a processing aid. In the case of the prepreg application, of course, that doesn't apply, but it's an additional benefit. So we tend to actually interact both on a processing point of view with with blade shops and then with designers on the more structural performance. So sorry, I've just lost my mouse. If we look at the various areas in the blade, you can say there's simplistically 3 areas: the webs, and then the shells, and you can break the shells into the root and shoulder area and the shoulder to tip area. So in the webs now, I think it was really originally PVC materials, sort of 60 to 80 kilo, and then it's really transferred to typically around 100, 115 kilo density PET materials. And of course, these make up the box section of the design. In the shell, you have the root to shoulder area, which is really, the thickest section area of the blade. And there's a lot of forces that come into being here. Balsa, has been a default for many people to use because of the properties, the high compression modulus properties of balsa. PVC was really quite expensive, so to use anything comparable, it would really be such a significant cost, although some people did use that. You could engineer out that disadvantage, and some suppliers did, but in the case of infusion designs, this has probably been a major shift of late, where PET has actually come in as a replacer to balsa, which has been quite a significant paradigm shift between material types. Because I think engineers, through their design preferences, really have got excellent properties from balsa. But I think, as everyone knows, the market grew really significantly. And over the last 20 years, there's always been times when balsa has struggled to supply the market, really because you have a 5-7 year life cycle from seedling to a tree. So if you don't plan ahead what's happening in the market, if you can indeed predict that, it becomes really hard against obviously a synthetic material. So, in the recent years, balsa became really challenged to supply. Designers were forced really to find alternatives, and PET entered into the bombs. So, this is a change that's occurring, I would say, OEM to OEM. Shell materials from the shoulder to tip, here obviously there's a lot more flex in the blade. And typically this is where, shall we say, a synthetic core material has been used to complement balsa in many of the infusion designs. And this progressively is got replaced by PET. I would say most of the Western OEMs today are using PET in their designs, whereas the Chinese suppliers, which of course are, over 40% of the global market, still use PVC today, based on designs from Europe. This is the last slide. There's a lot of information on here, and it's probably the one we could sort of spend a lot of time on here. We built basically a model within Diab to try to show, the trends in material types against market demand. And it's maybe an interesting one that, of course, many companies would do for their respective products. So you have 3 lines going across, which correspond to the axis on the right-hand side, which is the installed gigawatts as published by Wood Mackenzie in their last Q4 report. So you have the bottom line is the onshore market. The next one up is a cumulative one with offshore, and then with repowering on top. So you can see here the change from the left to the right in here, and I'm sure Mikael and also Siemens, who talk later, are far better experts to talk on that than I. But you can see here the peaks here that I talk about, which of course generally have corresponded to the changes in tariffs. And what I've then plotted on here is effectively in cubic meters, or thousands of cubic meters on the left, is how the use of core materials have evolved in the way that I've just described. So if you go to the very, very far left, when the market first began, there were 2 Danish companies. One had a base around balsa, the other had a base around PVC. The market grew, and it seems funny to say it here, but this area here was considered a very high growth area. The whole market was challenged. They had to find alternative materials. SAN was introduced at the time as an alternative, and then PET also. But PET really only came in on pre-preg designs. So it grew and fell with the pre-preg users. And of course, as some of those then converted over to infusion, if you like, the material developed, and consequently the market really opened up. And you can see how PET has really come in as let's say, a disruptive technology. There is a slight difference in 2020, which you can see is an incredibly high bubble. It was, I think, 46% higher than any analysts had predicted. But of course, if you take a more average view, you can just draw a growth line progressively upwards here. But this bubble in 2020 was really a result of China feed-in tariffs ending. So consequently, a lot of the supply chain was in China, which then meant there was a lot of balsa used and a lot more PVC used. So this is, shall we say, a little bit of a one-off. Then going forwards, we enter this period now, which I'm sure we're all aware of. It's almost like being at a traffic lights on an amber. It's a relatively stagnant market. We all geared up for really high growth. And we're now waiting for this, this next growth to come as offshore and indeed repowering come in. And what's going to happen next? Of course, we can all take a view on this. My personal expectation is that balsa will remain there as a material, as a default for some OEMs. Maybe its relative market share will reduce, and effectively it's perhaps capped by the amount of available capacity that can be harvested. PVC, which as I said, was the original part of Diab, you can see, is still there, and maybe dwindles a bit quicker, or maybe comes back in if people want to use it on particular designs. But inevitably PET will grow significantly. There's been a huge capacity put in, both by us and our competitors. So the expectation is, you can say, there will be some movement between PET and PVC here, and also between PET and balsa here. And I think a lot of that also depends on, you know, who are the winners in the market. So if one particular OEM wins a contract and their designs call up balsa, for example, then it will obviously have an influence on the growth. But I think in many ways, PET, shall we say, ticks many of the sustainability aspects going forwards. So I think, you know, that change has already been made, and maybe we look at what are the next generations of those. So Anders, I haven't been keeping a note on my clock, and I suspect I've probably overrun, so I should stop there and ask how I was doing on time.
Yeah, you're pretty much okay on time. It's no concern. I'm a bit curious. I mean, the load cases and the general properties for a wind turbine is extremely complex, with all the different loads, temperatures, fatigue issues, and so on. And having this vast variation of the materials, has that been a challenge, or are the designs so, this is not over-engineered, but on safety margins, so that you can handle these kind of variations? Because I mean, the properties of PVC and PET and balsa are pretty different if you break it down a bit.
Yeah, I think, well, first of all, of course, we have Siemens presenting in a moment, don't we? And I think they're probably in a better position, Anders, to answer that than me. So I can make an attempt, and if I get it wrong, please correct me, you know. But I think from a design point of view, I mean, the beauty of composites in general is they're inherently flexible, aren't they, in design? So there are various ways to, shall we say, achieve the end result. I mean, I talked in here about having, you know, typically infusion designs with balsa and, shall we say, and lightweight density PVC, whereas others have achieved the end by just using, you know, 80 kilo PVC, but they've also, you know, used maybe carbon spars, additional areas of reinforcements. So I think it's just how the designer wants to work with the core material, the resin, and the fiber in here. You know, it is a combination of all those factors, actually. And I think it is a challenge, actually, because I think the really one of the big things that, of course, everyone is facing right now, and I think Mikael touched on this in his presentation, you know, these growth lines for the market here are, you would probably consider relatively conservative. You know, some OEMs indicate to us, you know, that this actually could be a 10-fold increase on what they do today. So, you know, if as we all hope, the climate situation moves forwards, and if that's the case, then it really, really challenges the scalability of what is quite, I don't know if I can say it, not in an inoffensive way, but quite an immature supply chain. There's a lot of variation. So if we really want to get out cost and get that scalability, there need to be some standardization, I think, around the variations I described. You know, because you come into sustainability, of course. You know,
I thought we'd address the sustainability later on when we come to the panel discussion here. I just saw that we should be moving on here. I just don't want to interrupt you. But many thanks, Ray. We'll invite you back into the panel discussion a bit later on, because I'm a little bit curious also hearing about the recycled PET that is mentioned there as a future trend. But let's move over to Greger Nilsson, who is the founder and owner of Blade Solutions. And this is extra nice, as you're also one of the companies within SWE-CIC. So it's especially honorable to invite you to speak. And you will be talking a bit about your company and repair of blades. Thank you for the introduction, Anders. Yep, from a green point of view, our part is expanding the life of the blade. And our area of knowledge is repair of the carbon heat mats and also doing cold climate repairs. I'll start with the carbon heat mats. In northern part of Scandinavia, you need some kind of heat in the blade to produce power in winter. And one way is to have a carbon mat on the leading edge. And if you look on with a infrared camera, you can see you have a hotter area here. And that's why to melt away the ice. And why it's good to melt the ice. This is a typical blade without some kind of heat. And you can see this turbine will not produce any power. So you have to wait until the temperature go down or go up, or you lose a lot of production anyway. But the heat system always needs some services, something is happened. And one thing that is, I will not say common, but if there are a lot of turbine, there will be some problem, and you can have some impact on the blade. And if something hit the blade, then you will have a damage, and the damage will also damage the carbon heat mat. And if you look on an infrared picture, you can see you have a hot spot around the damage. And the problem with that, the hotspots tend to increase in size because you have higher temperature, you have a degradation in the matrix, the epoxy or polyester of the blade. And another thing that is quite common is you have a lightning strike that hit the heat mat instead of the lightning system, and then you also have a damage on the carbon mat, and so you have a hot spot around the damage, and you have to do some repairs for this. But the tricky part is to find the damage. That's we use long range infrared camera, so we can stand on the ground and scan the blade. A typical inspection takes half an hour, and what we look for is some variation on the temperature of the surface. And if we find some variation, we'll go up and look at the blade directly. This is a lot of repairs we have done over the years, but a carbon heat repair is very time consuming. So it's good if you can find the damage soon before the damage gets too large. And to develop repair methods, we do a lot of specimens in our laboratory where we create damage. We also, if we have every damage is not the same. So on regular basis, we train how to repair a specific damage before we do it up tower. I will go back. And this is, we have also developed 2 patents in this area. The other part we work with a lot with is doing cold climate repairs. Why do we want to repair in cold climate? if you find a damage in winter, maybe you have to shut down the turbine. If you have a structural damage, then you maybe have to shut down the turbine half a year and lose half a year of production for a summer repair. If you think it's a laminate, if it's minus 20 degree outside and you have minus 20 degree here on the surface, in the interface between the laminate and the repair, it's impossible to do the repair. If you do, you have to put some heat in it. Normally you put heat from the outside, but that means then you have a variation of the heat through the repair part. So if you're going to do a vacuum infusion for a structural repair, you will have different viscosity depending on what temperature you have in the specific part of the repair. That's why we put a typical blade heat system in the repair part. We have the laminate here that there are some damage in, and then we're going to put some repair material on top, and then we have a carbon layer here in between, a direct contact to the interface between the repair patch and the laminate. Then we can put the vacuum bag on it, and then we connect it to power, and then we can control the exact temperature in the repair here. So during the infusion, even in this case we had minus 15 degree outside, and we just put the power we wanted. So we have something like 20 degree during infusion. We want the same climate as in the blade factory, and in this case we have it. Inside here we have blade factory conditions, so we can make as good repairs as in a laboratory, even if we do it up tower in minus 15 degree. And after the vacuum infusion, we have a curing and a post-curing process, and this is a thermal picture from the post-curing where we have something like 70 degree. This is our resistive vacuum infusion. If we have minus 20 degree outside, we have exactly the temperature in the interface that we want, depending if we do the infusion, curing, or post-curing. We just set the power, the desired power, to get the right temperature. This technique is developed for repairing fiber wrinkle defects. It is a quite common defect when you make blade that you got some fiber wrinkles and you don't find it in factory. So after some years, you will find a crack. In this case, we go down and find this crack. If we remove the gel coat, we can see that we have a crack here, and we have some delaminations. And so it's quite important to repair this as soon as possible before we get the crack growth. And if you look, this is from the inside of the blade, you can see the same thing. You have some delamination around the crack here. If you don't repair, you can lose the blade. This is another blade that we inspected that wasn't repaired. So this blade had to be removed. You lost the whole blade from a similar start, I think. This is where we do the vacuum infusion. And here to the right, see the temperature during infusion. We have 25 degree. And after the infusion, we increase the temperature for the curing. So we have around 50 degrees for the curing, and we end up with a post-curing process where we have 70 degrees.
This is the result. You can see the connections point to the carbon here, and here you have the repair patch. When we have finished our repair, it will look like this. And this turbine could now be running some extra months because we did the repair in winter time. And that was the end of my presentation.
Okay, thank you, Greger. I'm curious on your typical work day. Doesn't sound like I guess that when the weather is good, it can be nice, but I can imagine that you have some harsh days as well at work.
It's not every day. It's like this, I would say. In some, we also have a tent, so we can have a tent around us when we are working. So after some hours, you forget where you are. You just focus on your topic.
Okay. But from a customer point of view, the cost-wise, do you have an assumption about what the cost saving is? Because I can imagine, that a tremendous cost saving to be able to repair it like you're repairing it, comparing to being able to take down the blade and repairing it on the ground.
Yeah. That I think repairing on the ground is too costly. Then you remove the blade instead.
Okay.
The crane cost is too high. So if you can't do up tower repair, then you change the blade instead.
Okay.
I think anyway.
Okay. And do you have to have different solutions for different producers? Because just listening to Diab's presentation, I mean, there are a lot of different ways of building the blades.
No, we are actually repairing glass fibers, so we are not depending on.
So it's the same process basically.
It doesn't. In this case, on these slides, you saw a balsa core problem.
Exactly.
But it doesn't matter if it's a PVC core or it's a glass fiber repair.
Yeah, but I guess that there are different matrices as well.
Yeah, but we use epoxy, and you can use epoxy on everything.
Yeah. Okay. Good. Thank you then. Thank you, Greger.
Thank you.
So moving over to today's final speaker, we will be listening from Khaalid, Mohamed, who is the material engineer from Siemens Gamesa on blades, and you'll be talking about RecyclableBlades, which has been a lot of hype around, I have to say. So this is going to be very interesting.
Yeah, definitely. Thank you very much, Anders. First and foremost, thank you very much for inviting me to this Composite talks session to represent Siemens Gamesa Renewable Energies and discuss how we are working with sustainability and circularity. As you mentioned, I'm working out of the Aalborg office in the materials team, working as a materials engineer. With a primary area of focus within reinforcements, both in regards to glass fiber, but also carbon fiber. And I would like to start off with a very, very brief presentation of Siemens Gamesa. Siemens Gamesa is a company who has more than 40 years have worked within the wind industry and have in many aspects been considered a pioneer and a market leader and still is. We span a total of 26,000 colleagues around the globe with various production sites also for the production of onshore and offshore wind turbines. And we have installed more than 110 gigawatts globally in collaboration with our customers and continue to provide clean and affordable energy to keep the lights on across the world. And as mentioned earlier, we are producing, of course, both onshore and offshore wind turbines and have a very strong foothold in both business areas. On top of this, we also have a very strong service business unit that ensures the continuity of energy supply, both by our own turbines, but also other OEMs. And finally, some global key facts. Of course, over 110 gigawatts installed globally, more than 26,000 colleagues around the globe, and also a portfolio that covers all requirements for, let me just, requirements both for onshore and offshore wind turbines. RecyclableBlade, which I know or I hope that most of you have heard about, is news that we broke early last year, I would assume, with a breakthrough technology for blades recycling, as we believe. It was essentially a blade produced with a recyclable resin that we think is going to be where the industry is headed, and a great step in terms of circularity and also recyclability within the wind turbine industry, especially in regards to blades. So to give you an idea of the recent developments and current sizes in the industry when discussing blades, I here present a brief overview of some of the milestones from the last 30 years. Most noticeably is the first project that was kickstarted for the offshore industry in Vindeby 1991, where a cumulative of 5 megawatts was installed. And what you can see is that the average rotor diameter, or the rotor diameter of the blades turbines installed, was around 35 meters long. That accounts to approximately 15 meters long per blade. And comparing that to the recently announced blades by Siemens Gamesa with a rotor diameter of 236 meters with a blade size of 115 meters. So there is no sign that this trend, especially the going upwards in terms of the rotor diameter, will stop for the foreseeable future. Thus, we can even expect even bigger blades can and will be produced for the offshore market. This is, of course, also something that we need to take into account when discussing possible solutions for recyclability and circularity within the wind turbine blades, the sheer size of the matters that we are discussing here. So what is the current situation? As presented in the earlier slide, the first offshore wind turbine farm was installed in 1991. And it is estimated, at least here in Denmark, that 50% of the existing onshore wind farms in DK alone are more than 15 years old. Some of them already approaching the end of life and decommissioning time. And looking at the schematic of the average life of the onshore wind farms, on the left, we can see how that spans across various countries within EU. And also looking at the infograph on the right, we can see that it is estimated by 2050 that composite waste from wind turbine blades is expected to reach 2 million annual tons by 2050, with a forecasted cumulative waste of 43 million tons. And a bit about the future and the growth that we are looking towards, with the strong focus from EU, especially on a green turnaround and to become the first climate neutral continent by 2050. Offshore wind is expected to play a vital role here. This obviously means a large jump and growth in the installed capacity by 2050, in which offshore installed capacity expected to grow to 450 gigawatt globally, or in Europe, sorry. This, of course, you can imagine that means that a lot of blades will be produced, also demanding us to think ahead in terms of recyclability of these blades, with the estimated values of metric tons that were to be decommissioned by 2050. And blade end of life is a very important aspect when discussing blades. And it's also an aspect where we only have a few options currently available. I'm sure you all have seen the horrifying picture on the top right of the slide. Of the wind turbines blades filling up the landfills, which unfortunately is where most blades are discarded. Obviously, disposal in landfill is not a desired option and is currently banned in a lot of countries. An alternative solution is also the co-processing in cement kilns, where glass fibers can be used to reinforce concrete. And also we have the reuse of components in architecture. But of course, all these solutions are limited and not the exact desired option that you would see for a decommissioned blade in terms of recycling. So the desired option is, of course, recycling. And the key will be the removal of the matrix material under mild processes conditions to allow for the recovery of all the materials, constituent materials that goes into the composite in a good condition. And this allows for all the materials to be reused, perhaps for the same application or other application, and that the value of the materials is kept at a very high level. And then alternatively, you also have the upcycling option, where you are able to use some parts of the wind turbine blades for other purposes, like we have done here in Aalborg, using that as a bite shed, for instance. So the recyclable blade, a breakthrough technology, which I truly believe for blades recycling. The recyclable blade is a pioneering solution, I would say, which enables us to do exactly what the desired outcome in terms of blade end of life would demand, and that is the separation of fibers and matrix to be recycled and reused. The resin itself uses a modified epoxy system, which allows for the recyclability of the thermoset resin by allowing the separation of the composite materials. This, of course, results in that the recovered material retains a high property level and can be used further for other applications. And just looking briefly at the technology behind the recyclable resin. The technology is different, you can say, compared to the conventional epoxy resin in the way its molecular structure of the resin system is composed. Despite being processed in the same way as conventional epoxy resin, it is different in the sense that it has a cleavage point which is introduced by means of a reactive group in the hardener to the resin system. And this subsequently allows for the, I would say, decross-linking of the resin system once it's introduced into some mild acidic conditions at an elevated temperature, where the cross-linked networks are actually broken, and thereby the resin is dissolved. Yes, then the obtained resin afterwards can then be used as a thermoplastic and then reused further for other applications also. And it should be emphasized that the resin is absolutely in no way different than the conventional epoxy resins. We process it in the same way with our integral blade technology and have exactly the same design criteria pertaining to all other epoxy solutions. And it's, as mentioned, no structurally different from other current solutions. And it also brings along this added benefit of being recyclable, and you're able to dissolve the resin and obtain the individual components of the blade separately. And yeah, It's used in our wind turbine power plants, and it's no different from any other blades that we have previously produced. And just to give you a brief overview of the step-by-step process, we can see that once a blade is still commissioned, it is then introduced to our to a recycling phase where you immerse the blade or cutouts or sections of the blade, however you want to treat it, since as we discussed, the blades are upwards of 115 meters now, and with no signs of slowing down in sizes at least, and dissolve the blade or the resin in acidic conditions at elevated temperature for a few hours. And that allows you essentially to reclaim the separated components that went into the composite manufacturing, and having them as separate layers, glass and core material. And essentially that would also feed into this circularity aspect of having the chance to use the material for other purposes, or even within the same industry in another turbine. And so same means same. Whenever we say that the structural properties of this resin is no different from the other resins that we also have, this is also supported by the structural analysis that we did on this resin system. And as you can see on the right hand plot, we have a fatigue plot tested for a laminate, a shell laminate, using the recyclable blade, and also using a conventional blade resin that we use. The purple line being the recyclable blade resin, we can see is a bit on top of the gray one, which also shows that you get a slight the higher capacity perhaps, but on up as a performance on par with what we were expecting. And looking at the table on the left, we can also see different parameters in terms of the structural properties, with a small increase in both the tensile strength and modulus, and also the flexural strength and modulus when using this resin system. So it's overall a very large leap, I would say, in terms of how we are manufacturing, and also a paradigm shift of some sort in the manufacturing of wind turbine blades, in the sense that we are actually able to use thermoset resins and also be able to separate them afterwards. And as a concluding remark, I had a talk with Anders last week, and he mentioned that the setup that we were aiming for in Composite Talks was very much a TED Talk-like setup. And from looking back at all the TED Talks I had watched, I was always left with a sense of inspiration and motivation and a direction. And in my attempt to do so, I would like to present a proverb in my parents' native language that goes along the way that a single finger does not wash an entire face. And using that in our industry, we need all interested parties to actually act along the same way, to be able to push this agenda of recyclability and circularity within our industry. And that is right from the end consumer sitting within their homes, their suppliers, OEMs, our suppliers, and very much also academia, who also has a very great stake in this matter pertaining to all of us. And with those words, I would like to conclude the presentation, and thank you very much for listening in.
Thank you, Khaalid. This is really interesting. We got one question from the chat, which was one that I had on my table as well. Is this a technology which will be applicable to your competitors or in other composite industries?
Yes, that would very much be a technology open for everyone. I think it's developed in collaboration with a supplier, and yes, it can also be used in other industries for other applications, also other than wind turbine blades.
Okay, thank you. And another, I don't know if you have that detail, but from I wonder if you've done any life cycle analysis which compares to, so say, what the LCA effect is of your solution compared to the alternative way of recycling a blade.
Yeah, I'm sure those studies have been conducted, but I actually don't have them with me right now.
Okay.
But something that we can share for sure. Yeah.
Okay. One direct question here was: is it possible also for polyester to break it up?
Yeah, so the chemistry in this is directly pertaining to the epoxy systems, right? So it's and if it can be incorporated into polyester, that's a fairly good question. I would direct that to our epoxy experts within the company, but yes, something to be looked into for sure.
Okay, thank you then. Thank you all speakers. We can, if you have the possibility of turning on your cameras, we can have a short little panel discussion. I can also mention that we intentionally meant to be 5 speakers. We had one cancellation a little bit late, unfortunately, and that was Modvion, who is producing modular wood towers, which was had to cancel. But I can inform you that they will be presenting at the LIDAR International Conference in Gothenburg on the 6th and 7th of April, which Linnea mentioned here. So that's an opportunity to listen to Modvion, and at that same conference also we'll be talking about RecyclableBlade as well. Harald will be, forgot his last name, Stecker, will be speaking about RecyclableBlade at the conference there as well. But great. Oh, Christian has joined us as well from Diab. But first of all, a little bit around sustainability is always a hot topic. Now we talked about recycling here of the blade, but in general, it's what is the view regarding using more natural fibers or recycled materials and so on? Ray, you had recycled PET there as a cliffhanger in your presentation.
Yeah, I mean, I think. Shall we say, I mean, it was really interesting actually listening to the presentation from Khaalid, of course, there, which is really actually shows one of the challenges about how to separate those materials out. So I think on the PET side now, I mean, first of all, we of course are having to produce an awful lot of data for OEMs now to support them with the sustainability. So we're having to calculate, carbon footprints for different supply routes of material. And of course, if you look at it from a base source, the largest generator, of course, is at the point of production, first of all. So you have the virgin grade PET, which is lower than its PVC equivalent. And one way to improve that further, of course, is to use recycled materials, or which has been done for some time, and we start to do that as well. And that's, I suppose, most people know, in the form of using plastic bottles. And then I suppose the next thing is, down the line, what other alternatives are there? I suppose non-oil based alternatives, for example. So I think perhaps in the same way that PVC was on a journey many years ago to where it is now, I think PET is on a similar journey on that base point.
Okay, thank you. What is Siemens Gamesa? Is that, so say, natural fiber or bio-based epoxy systems? Is that something that you guys are looking into as well?
Yes, most definitely. I think so sustainability is, of course, a big agenda across the board, and so natural fibers, I think, also have seen some traction over the last couple of years, with a lot of academia looking into how you can use that in conjunction with common epoxy systems and reinforcing that in composites. So that is for sure something that we are looking into. but you also have the design drivers, right? So building bigger and stiffer blades also requires stiffer materials. So there's the balance where you need to find what you can actually use and also think into consideration what sustainable materials are out there that can fulfill your requirements.
Okay, cool. The issue of size is always interesting here. That we're now at, what was it, 115 meter blades. How far will that go? And what are the requirements, or what are the challenges to increase the size even more? I understand the logistics of that part, but from a technical point of view, and producing blades that are bigger.
Yeah, so a lot of people have in the past predicted what the size limit would be for wind turbine blades. So I will not make an attempt because they have all been proven wrong. So that's the first step. In the second, I think in terms of what the size limitations could be, you obviously have a driver in terms of the stiffnesses of the blade, right? So tip to tower clearance is something that is very important to look at when looking at bigger and bigger blades. So that is the one I can think of right off the bat, especially. Yeah. But then you also have the logistics and manufacturing sites and transportation of these big blades, right? So that is also something that factors in, and also the what energy can you actually make compared to other factors that you can perhaps tune in the wind turbine in total.
Yeah. Mikael, the progression that you showed for reaching the targets that Vattenfall has, there are a lot of wind turbine blades that needs to be produced, and I expect that one of the challenges that you have is being able to where to place all of these wind turbines. What do you see as the biggest challenges to reach your targets?
Well, I mean, it is of course a challenge to find the sites. Most of our growth in recent years has been in offshore, but we're also now increasingly looking at northern Sweden, of course, because of the upcoming demand. But we clearly see, and I guess that goes for any kind of infrastructure in this case, that it is increasingly difficult, both from a public acceptance perspective and also from environmental permission perspective, to do this transformation.
Yeah.
So that's probably more of a challenge than the technology in itself. I would say the technology needed for this transformation and the economics actually looks quite good. That's not the biggest hurdle anymore.
Okay. We have a question from the chat here. Are the material suppliers trying to meet the need for sustainable materials, for example, carbon fiber? I don't know who can answer that question.
I can give it a shot. I mean, when comparing this industries that produces these materials needed for the products, they differ quite a bit in their complexity. Steel is, for example, a quite integrated, simple supply chain in a way, whereas petrochemicals could be extremely complex, and introducing something new in a complex supply chain is pretty difficult. I mean, there is no easy scale of doing that, so to say. I mean, we know today that you can make, for example, methanol to olefins in 1 million ton per year size, but there is no methanol, no green methanol. So going that route is a bit tricky. There is no large scale carbon capture or biogenic sources that can supply it with carbon. So a lot of things need to happen at the same time, and I sometimes get the impression there is some anxiety to it, that to form this, the more complex the value chain becomes, the more tricky it is to form alliances and vertical partnerships to do this.
Fully understand. Linnea, have I missed any questions here?
No, I think we're pretty. I saw that there was a question in the beginning that I believe Mikael. I'm super interested in Vattenfall's promise not to leave any wind turbines in land bans, and what options for recycling or reuse of the composites that they are looking forward to into the close as well as long term. But I believe that you replied to that in the chat, Mikael.
Yeah, I mean that's an ongoing job in our wind division, and I don't have the latest details there, so I would prefer not to speculate at this time.
Yes, I think we are pretty. The questions have been answered. So yeah, I think it might be time. It's only 5 minutes to go as well, so I think it's time for the wrap up.
Yep. First of all, I just want to thank all of the speakers. It's been great to have you on board. A good combination of the whole value chain as we started off. I just also forgot to mention that we actually have 3 finalists at the SWE-CIC Innovation Award, both or Diab for sandwich area for aerospace, and then within renewable energy, actually Siemens Gamesa with the RecyclableBlade and Gregor are actually competing on the first prize in the same category there. So and that will be announced on the 26th of April. I don't know why it's not announced at the same time at SWE-CIC, but apparently it's announced 1 week before. But in general, I just want to thank everybody, and it's been an honor to be able to moderate this. It was really interesting. And then Linnea, you will upload the recording.
I will.
And I think that there was actually a question here if we will be distributing the actual presentations. Do we have that plan? Or are we just uploading the recording?
Yes, at this time, I will only be uploading the what's it called?
The recording.
But that's up to you, the presenters. If you would like me to distribute the presentations, you can just send them to me, and I'll distribute them to the participants. So hopefully.
Okay, but then thank you for today, everybody, and looking forward to our next composite talks. Which theme do we have, Linnea? Forgot it at the moment.
I think it's the future of mobility.
Yes, that's right. So the future of mobility. So we're looking for that. We're aiming for May for that composite talks. And
in the autumn, we will have one on architecture and one on furniture design.
That's right.
I think if I remember wrong.
I think you're right. I think you're correct.
So yeah, thank you everyone for participating. Yep. Thank you for speaking. It's been super interesting.
Yes. Thank you, everybody, and have a nice weekend. Bye bye.
Thank you.
Yep.
Thank you very much.
Bye.
Thank
you. Goodbye.
Bye.